Welcome students to today's lesson. We are continuing with probability, and today we want to discuss about mutual independence. So this section is a bit technical. We will need to know the conclusions, though the arguments we use to reach them are not so important. We saw in the coin tossing example above that it is possible to have three events: event A, event B, event C, so that A and B are independent. B and C are independent, but A and C are not independent. If all three pairs of events happen to be independent, can we then conclude that the probability of A intersection B intersection C is equal to the probability of A dot probability of B dot probability of C? At first sight, this seems very reasonable. In Theorem 3, we only required all pairs of events to be exclusive in order to justify our conclusion. Unfortunately, it is not true. So if we take an example in the coin tossing example, let A be the event, first and second toss have same result. B be the event, first and third toss have the same result. And C, the event, second and third tosses have the same results. You should check that the probability of A is equal to probability of B, which is equal to probability of C, and that is equal to a half. And that the events A intersection B, B intersection C, A intersection C, and A intersection B, B intersection C are all equal to head, 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 tail, 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 with probability of a quarter. Thus, any pair of the three events are independent, but the probability of A intersection B intersection C is equal to a quarter, and the probability of A dot probability of B dot probability of C is 1/8. So A, B, C are not mutually independent. The correct definition and proposition run as follows. Let A1 up to An be events. We say that these events are mutually independent if given any distinct indices I1, I2 up to Ik, with k greater than or equal to 1, the event. So we have I1 intersection I2 intersection up to Ik minus 1 and Aik are independent. In other words, any one of the events is independent of the intersection of any number of the other events in the set. So by taking the example, let A1 up to An be mutually independent, then the probability of the intersection of A1 and A2 up to An is the same as the probability of A1 dot with the probability of A2 up to the probability of An. Now all you really need to know is that the same physical argument that justified that two events, such as two tosses of a coin or two throw of a die, are independent, also justifies that any number of such events are mutually independent. So for example, if we toss a pair coin 6 times, the probability of getting the sequence head, head, tail is a half raised to power 6, which is 1/64, and the same would apply for any other sequence. In other words, all 64 possible outcomes are equally likely. So this marks the end of our today's class. Let's again meet in the next class.